Method 2. This method 2 is called as the axiomatic approach. This method is a axiomatic approach applicable for both finite and infinite sets. This is an axiomatic approach for studying the potential of a set approach, and is also applicable for both finite and infinite sets. In this method, we require two important sets and three axioms. Two important sets we require. A function, a concept of function, that is 1-1 onto and 1-1 correspondence, and three axioms. In these methods, we need three things: two important sets of functions, concept of function, and three axioms. What are the two important sets? That is set of natural number 1, 2, 3, 4, ... and segment, initial segment of natural number. This is called initial segment of natural number as 1, 2, 3, 4, ... L. Why it is called initial segment? For example, if this is a line, and if we cut this line, this portion of line is called the segment of line. Segment of line AB is called the segment of line. Similarly, if you have natural number, set of infinite natural number as 1, 2, 3, 4 till infinity, then the initial segment of natural number, for example here n is there, ... the initial means first n natural number. This segment of natural number is called Sn. This is called initial segment of natural number. For instance, if I say first n natural number S5 as 1, 2, 3, 4 and 5, this is the initial segment or segment of natural number or segment of natural number. Similarly, S6 as 1, 2, 3, 4, 5 and 6. This is also segment of natural number. Not all natural numbers, but a segment of natural numbers. First 6 segment of natural number. This is first 5 segment of natural number. Therefore, it's called initial 5 segment of natural number. This is called initial 6 segment of natural number. So, two important sets we require in method 2, that is set of natural numbers, infinite natural number, and initial segment of natural numbers. And second, a concept of function we require, and third, three axioms. Now let's discuss the three axioms. Let's discuss the axioms, three axioms. Axiom 1 states that let set A and set B are two non-empty sets. If there doesn't exist if there doesn't exist onto function that is a surjection. Let A and B are two non-empty sets if there doesn't exist an onto function or surjection between the set A and B, that is from set A to B. We say that B has more potential than set A. and we write it as potential or size of the set A is less than the size of the set B. In other words, we can say that if there doesn't exist a function f from set A to set B, then we say that potential of A is less than the potential of B. Axiom 2. Let A and B are two non-empty sets. If there doesn't exist a one-one function, from A to B, one-one or injective function. If there doesn't exist a one-one or an injective function from set A to set B, we say that A has more potential than that of set B. That is, set A, potential of set A is greater than the potential of set B. That is, the cardinality of set A is greater than the cardinality of set B. Third axiom, this is the last axiom. If there exists a one-one function, one-one and onto function from set A to set B, we say that A and B have same potential. That is, set A, potential of set A is equal to potential of B. Now let's deal with the finite set using method 2. Finite set. Now we're gonna deal with finite set, deal with the potential of finite set using method 2. Finite set. A non-empty set A is said to be finite if and only if the set A is similar to initial segment of natural n for some n, and n is called the potential of the set A, and is called the potential or the size of the set A, or the cardinality of the set A. Let's take the definition again. A non-empty set A is said to be finite if and only if A is similar to initial segment of natural number, or A is equivalent to initial segment of natural number for some n. Then we say n is the potential of the set A or the cardinality of the set A. A note: by definition, empty set is finite, and its cardinality is 0. That is, the size of the empty set is 0. Let's take an example. If I define a finite set A as A, E, I, O, U, and let's discuss about the potential of A. If I defined a function between the initial segment n of natural number and set A, this is initial segment n, that is, okay, let write down all the elements of A, E, I, O, U. How many elements there? How many elements set A has? 1, 2, 3, 4, 5. Therefore, we'll take initial segment set of natural number as 5. 1, 2, 3, 4, and 5. Let's define a function from initial segment of natural number 5 to set A, such a way that 1 is mapped to A, 2 is mapped to E, 3 is mapped to I, and 4 is mapped to O, and 5 is mapped to U. Here we can see that all the elements of this first set, let me denote this first set as C. All the elements of the first set C is assigned to all the elements of set A, and they are distinct. Since they are distinct, we can say this function f is 1, 1. And since all the elements of set A has pre-images in set C, we say this function is onto as well. And since there exists a function that is 1, 1 and onto between the set A and set C, we say the potential of set A is equal to the potential of the set C, that is equal to potential of the initial 5 segment of natural number. And since the cardinality or the potential of this set S 5 is 5, we can say that potential or the size of set A is equal to 5. This is how we communicate the potential or size of a finite set. Now for infinite sets. Now let's discuss the potential of infinite sets using method 2, that is the axiomatic approach. A set is said to be infinite if it is not finite. If it is not finite, that is neither empty nor similar to initial segment of n for all n. If this what is infinite sets? A set is said to be infinite. If it is not finite, that is the set is neither empty nor is similar to Sn for any n. Then we can say that set is infinite set. Example: set of natural number, power set of natural number, Cartesian product of natural number, n cross p of power set of natural number, set of rational number, set of real number, interval of real number, etc. So how to define the cardinality of the infinite set? That is how we can deal with the cardinality of the infinite set. Since the number of elements in an infinite set is infinite, we cannot have a finite cardinal to measure the potential of the infinite set. That is, we do not have the cardinal of natural numbers to define the potential of the infinite set. There is no infinite set is similar to Sn for any n. Let me write down what I have said. Since the number of elements is in an infinite set is infinite, we cannot have a finite cardinal to measure the potential of an infinite set. That is, we do not have a cardinal of natural number. A note that let me write it as a note. No infinite set is similar to Sn for any n. No infinite set is similar to Sn for any n. So how can we study the potential of an infinite set, or how can we compare the potential of two or more sets, two or more infinite sets? So for that, mathematician came up with the concept of transfinite number. They introduced a new system of number, that is system of transfinite number. Therefore, we came up with a new concept, that is transfinite number. That is, we came up with a system of transfinite number. System of transfinite number. This is a new number system that is called as system of transfinite numbers. This is called as collection or set of transfinite numbers. So what is a transfinite number? Transfinite number is a number that quantifies the notion of infinity. We have two types of transfinite number. That is Aleph null, the symbol for Aleph null, and second is continuum, C. This is called as continuum. And this is called as Aleph null. Aleph null or Aleph naught. This is used for countable number, which we gonna study in the next lecture. This is called as countable number. This is this symbol, or this Aleph null represent countable number, countable infinite number, and this symbol, this continuum, represent uncountable number. Using this parent transfinite number, we derive more transfinite number. Using these two symbols, or using these two transfinite numbers, we derive more transfinite numbers. These two transfinite numbers are called parent transfinite numbers. Using these two parent transfinite numbers, that is Aleph null and continuum, we derive more transfinite finite numbers. Second, there is no transfinite number between Aleph naught and C. Second fact, this is fact 1, this is fact 1, this is fact 2. There is no transfinite number between Aleph null and C. Fact 3, there is only one countable transfinite number, one countable transfinite number, that is Aleph null, and there are infinite uncountable transfinite numbers. Therefore we can say there are only one countable numbers of the type Aleph null and infinite uncountable transfinite numbers. This is fact 3. From fact 2 we can state fact 3. From fact 2 we can say fact 3, that there is only one countable transfinite number, that is Aleph null, and infinite uncountable transfinite numbers. This fact 3 follows from fact 2. From fact 2, fact 3 is followed. If I define a set of natural number n, 1, 2, 3, 4, and infinite set of even numbers as 2, 4, 6, and 8, If I define a function from n to e in such a way that 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6, in such a way that if y is the elements of all the elements of e is represented by y and all the elements of n is represented by x. So if I define a function from n to e, if I define a function f from n to e in such a way that all the elements of e, that is y, is 2 times x. Here x is the elements of the natural number, x is the elements of natural numbers. Since here you can see that all the elements of natural number is mapped to all the elements of e. Therefore this function f is 1, 1, and all the elements of e has pre-images in n. Therefore this function is onto as well. Therefore we can say the cardinality of natural number is equal to the cardinality of even number, that is Aleph null. We are gonna discuss about Aleph null and continue in the next lecture in more detail. So right now that's it for now.